Right, let's have a look at question 10. This is the core practical. This is the measuring G, measuring acceleration due to gravity, core practical. This is one of the methods, because I think there's three methods you should know about. This is the trapdoor method where we use an electronic timer. So, what's all this about? Right, if you remember, measuring G by varying the height and measuring the time, we're going to use this equation, aren't we? We're going to use S equals ut plus a half a t squared. S is the height dropped through. U sub 0 because it's dropped from rest. So this becomes a half g t squared. Now, what have we got on the y and x axis? We've got t squared on the y and h on the x. So we need to rearrange this. Okay, we're going to rearrange this to make t squared the subject. So t squared equals 2 over g times h, isn't it? So we've got t squared on the y-axis. We've got h on the x-axis. So we've got 2 over g. That's our gradient. Our gradient's equal to 2 over g. So if m is 2 over g, then g is 2 over m. That's how we calculate g in this case. Right, so what do we need? We need a straight line of best fit, don't we? We're going to use our cheeky straight line tool in Cami. So let's have a little look. Let's try and get this. That'll do. That'll do. Right, what do we got? So with the gradient, we want change in y. So we're going to go up to here. We're going to start from here. And we're going to go up to here. And we're going to start here. So let's have a little look at this. Gradient equals 0.39 minus, let's go for 0.05, give or take, over 1.80 minus 0.40. So what's that giving us as a gradient? Let's have a little look. So 0.39 minus 0.05 equals, divided by brackets, 1.8 minus 0.4, close brackets, 0.243. That's the gradient. We're going to put it into this equation here. So we're going to go 2 divided by that, 8.24. 8.24 is a value of g. So where should we write that? Okay, let's write it down here. So we've calculated from our graph that the gradient is 8.24 meters per second squared. Okay, right. We want to comment on that. This is what this question is all about. We've got to comment on the conclusion. So an obvious place to start would be percentage difference. Okay, so the percentage difference in G is going to be actual minus measured, was 8.24, yes, over actual. So what's that giving us? %. So we have a percentage difference of 16%, which is not bad. It's not brilliant. Okay. Now we need to work out from our estimations of uncertainty what our uncertainty in G would be, and then make a comparison with our percentage difference. That's how you evaluate a practical. That's how you see, or that's how you conclude whether the practical is good or not. So it gives us a very, very important piece of information here, or piece of advice, which is this. You may assume that the percentage uncertainty, not the difference, this is the percentage difference. You can assume the percentage uncertainty in G is the same as the value from one pair of readings. So it tells us at the start, doesn't it? Tells us at the start of the question that the percentage uncertainty in T is plus or minus 3% and H plus or minus 1%. Okay, so let's go back to our equation here that we're using. Okay, let's start with that. Where are we? So H equals a half GT squared. Going to rearrange this to make G the subject. So G is equal to 2H over T squared. Right. We want to know the percentage uncertainty of this. We know the percentage uncertainty of this. We know the percentage uncertainty of this. So we need a compound uncertainty. Right. The percentage uncertainty in H is 1%. Now, the percentage uncertainty in 2H is still 1% because it's percentage uncertainty. We don't double it because it's percentage. Okay, so the percentage uncertainty in G is equal to the percentage uncertainty in H. Now, even though we're dividing by, we still add the percentage uncertainty in this to the percentage uncertainty in this. We always add. However, because it's T squared, we've got two lots of percentage uncertainty in T. So we add together two lots of percentage uncertainty in time. So that gives us 1% plus two lots of 3%. So our percentage uncertainty from just a single pair of points is 7%. Right, comment now. We've got a percentage difference of 16%, but an uncertainty of only 7%. So we're not quite there, are we? We're significantly off. So an obvious comment would be there's other uncertainties in this practical that we have not taken into consideration and that we maybe want to look at to improve our method. Okay? Right. There you go. Core practical. Thank you.